Every millisecond, an autonomous vehicle processes a chaotic influx of urban data. The initial step is straightforward, identifying objects in a flat 2D camera feed. But vehicles do not drive in 2D. To plan a route or avoid a collision, the system must translate those flat pixels into a top-down 3D bird's-eye view grid. In this space, standard 2D bounding boxes become entirely useless because they lack the critical z-axis, depth. Modern perception systems attempt to build this 3D environment using only cheap, reliable camera arrays, stripped of explicit depth sensors like LiDAR. The system must map a flat 2D pixel into a 3D coordinate space using only the camera's internal calibration metrics. This geometric hurdle is formally known as the View Transformation Module, or VTM bottleneck. It is a mathematically ill-posed problem. Without LiDAR data, a single 2D pixel does not correspond to a single point in space. It maps to an infinite 3D projection ray. That creates infinite depth ambiguity along the camera axis. Faced with this bottleneck, engineers fractured into two opposing architectural camps, divided by which coordinate system dictates the math. The first camp relies on forward projection. This approach uses the 2D image plane as the source of truth, actively pushing feature data outward into 3D space. The second opposing camp uses backward projection. Here, the architecture establishes an empty 3D grid first, then casts rays backward to pull relevant features from the 2D image. The evolution of modern spatial perception is a direct architectural tug-of-war between these two projection methods, a conflict that has only recently been resolved by continuous spatial models that abandon rigid grids entirely. The archetypal forward projection architecture is Lift-Splat-Shoot, or LSS. During the lift phase, the network attempts to mathematically model depth uncertainty. It divides the camera array into a rigid set of discrete voxels and predicts a categorical probability distribution, a softmax curve, representing the likelihood that an object exists at each specific depth bin. In the splat phase, the 2D image feature vector is multiplied by its depth probability, then sum-pooled into the corresponding 3D voxel grid. The first mathematical flaw of LSS lies in the softmax operation itself. Softmax generates highly unstable probability distributions. A slight variation in pixel values can produce wildly different depth estimates for immediately adjacent pixels. The second flaw is computational. Imposing a rigid discretization of uniform depth bins forces the system to calculate values for vast stretches of empty 3D space. While the LSS matrix operations are highly interpretable, they yield an inherently sparse bird's-eye view grid. It cannot provide the continuous spatial coverage a high-speed vehicle requires for downstream planning. Backward projection architectures, like BEVFormer, were engineered specifically to eliminate the sparsity of LSS. Instead of pushing pixels outward, this method generates a dense grid of uniform 3D queries in the bird's-eye view space. The mechanism operates in reverse, projecting rays from these 3D queries backward onto the 2D image planes to sample visual features. This solves the empty space problem, but introduces feature smearing. Because multiple 3D queries on the same projection ray intersect the identical 2D pixel, they fetch the exact same image features. The network assigns identical data to points at vastly different depths. Backward projection guarantees a dense representation and ignores empty space, but it introduces severe geometric ambiguity because it operates without explicit depth awareness. Hybrid pipelines, like FB-BEV, attempt to merge the precise depth accuracy of forward projection with the dense coverage of backward projection. Phase 1 executes a standard forward projection module. This generates a highly accurate, but inherently sparse, initial BEV anchor grid. In Phase 2, the architecture identifies the unactivated blank grids within the BEV plane and explicitly targets them as new spatial queries. The refinement step then applies backward projection, mapping only these specific blank queries back to the source images. To fix the smearing issue, the network integrates depth consistency weights into this backward projection. This establishes a precise mapping relationship, ensuring distinct features are assigned to distinct depths. Bidirectional mapping proves a system can achieve both density and accuracy, yet the architecture remains constrained by the heavy computational burden of processing a rigid voxel foundation. Advancing beyond the hybrid model challenges a foundational assumption, the idea that 3D space must be divided into rigid, uniform grids to be computed. The first mathematical step away from rigid voxels is adaptive discretization. Methods like ADA-bins move adaptive partitioning directly inside the view transformation operator. Instead of fixed intervals, the network dynamically routes features by shifting bin boundaries per image based on actual scene content, forming a 1D soft Voronoi diagram. This adaptive logic leads directly to the ultimate continuous representation currently disrupting the field, replacing discrete bins entirely with 3D Gaussian blobs, an approach utilized in Gaussian LSS. The math translates seamlessly. Depth uncertainty derived from the 2D image converts directly into the spatial variance of a continuous 3D Gaussian distribution. By utilizing these continuous parameters, the architecture can deploy Gaussian splatting rasterization. It renders features directly onto the BEV grid, completely bypassing the slow, discrete sum pooling step. Treating the world as a series of continuous probability distributions inherently prevents the depth ambiguity of backward methods, while mathematically eliminating the sparsity of forward methods. The theoretical elegance of these architectures only matters if they can survive the brutal computational realities of real-time autonomous hardware. Querying every single backward ray or computing thousands of empty forward voxels introduces crippling latency, often yielding unworkable frame rates. This chart maps rendering speeds across these competing methods. By adapting fast 2D graphics techniques to render 3D Gaussian distributions, rasterization bypasses the traditional voxel bottleneck. We see a dramatic spike upward, from ray query methods operating at a fraction of a frame per second to continuous rasterization hitting 100 frames per second. In autonomous driving, computational efficiency is a physical safety metric. At highway speeds, minimizing view transformation latency is the literal difference between a safe maneuver and a collision. Resolving the view transformation module is what allows 3D spatial awareness to emerge from standard camera arrays. We are demanding that machines interpret complex, unstructured physical environments, like this crowded urban street, using nothing but visual data. The literature points in a distinct direction. The future of perception requires abandoning rigid, discretized assumptions of space in favor of continuous geometry and dynamic feature routing. As autonomous vision models converge on these continuous mathematical representations, they resolve the view transformation bottleneck, providing the scalable, real-time perception necessary for embodied AI to operate in physical space.